All right, thank you so much, everyone. It is Tuesday, June 6th here in Albuquerque, 10:15 a.m. Mountain Time. We are here for the Resolving Stars and Hunting Nearby Galaxies press conference. My name is Kerry Hensley, and I'm the AAS Deputy Press Officer. I am assisted today by Ben Casses, our AAS Media Fellow, as well as Sumit Kulkarni, our Astrobites Media Intern. Thank you so much to everyone in the room, on Zoom, and watching on YouTube for being here. Before we get started, I want you to take a moment to silence your cell phones if there's a chance it might make any sound. For our press conferences that happened yesterday, the press kit has been fully updated with the briefing videos, the press releases, and almost all of the presentation slides. So brief ground rules for how this is going to go. I'm going to very briefly introduce our panelists. We're going to hear from our three panelists in order, and we'll have Q&A for all three of them at the end. If you're watching via Zoom, please use that Q&A feature to queue up your questions while our speakers are talking. So as I said, this is the Resolving Stars and Hunting Nearby Galaxies press conference. Our first presenter, who I should show you, here we go. Say hello to Olivia. So our first presenter is going to be Olivia Gaunt from Tufts University, speaking on rare signals from stars in the Triangulum galaxy. Following Olivia will be Jim Jackson from the Green Bank Observatory, speaking on star formation triggered by an expanding bubble in the Nessie Nebula. So getting your fill of astronomical cryptids today. And our final speaker will be Stephen Walker from the University of Alabama in Huntsville, talking about X-ray observations of a group of galaxies falling into the Coma cluster. So with that, Olivia, if you want to go ahead and share your slides again.
Sure thing. Thanks so much. All right. Let me make sure everyone can see this.
Yeah, that looks great for us. Thank you.
Great. Thanks so much for having me. All right, so my name is Olivia Gaunt. I'm a second-year PhD student at Tufts University. I'm coming to you live today from Somerville, Massachusetts, although I wish I could be there in the room with you. Although this work has been carried out actually with UC Santa Cruz. I've been working with Dr. Raja Guhathakurta from UC Santa Cruz since 2020 in one of his multi-institutional research groups. So I've been really excited to be a part of that. And today I'll be sharing some of our work with you. So we're going to talk today about rare signals from stars in the Triangulum galaxy, or if you'd prefer a slightly more technical title, broad emission-lined luminous sources detected in the stellar disk of M33. So you'll hear me refer to these objects as bells throughout the presentation, and that's what that stands for. Oops, there we go. So the talk will be structured as follows. First, I'll give you a little bit of background, some context on our data, M33, which is the Triangulum galaxy, and a special class of rare stars called Wolf-Rayet stars. Then I'll jump right into observations. I'll present some of the interesting Bell's spectral features, and we'll do a quick time comparison and show one very interesting finding. Then I'll finish up with some conclusions, our findings, the implications thus far, and the future direction we're hoping for this work. Just minimize this. All right, so we'll start with some background. The first thing I'd like to address is where our data came from. We've been using the Deep Imaging Multi-Object Spectrograph called DEMOS, which is on the Keck 2 telescope. The Keck telescopes are a part of the Mauna Kea observatories located on the summit of Mauna Kea in Hawaii. I had the immense privilege to be able to go out there myself and use this instrument. And I was absolutely blown away by the respect that people have for the land and the environment there. So I just wanted to take a moment to address the importance of this land and the fact that we get to use it for this amazing science. Then I'll talk a little bit about the Triangulum galaxy, which is the galaxy of interest here. M33 is 2.73 million light years from Earth, which is very, very far away, but also considered relatively close. If you think about the Andromeda galaxy, we think of that as a very nearby galaxy. It's just slightly further than that, so it's still considered to be a local galaxy. An important number I'd like you to keep in mind is that it's estimated that about 40 billion stars reside in this galaxy. That's an important number. Hold on to it for the next slide. And because I study galaxy evolution at Tufts, I actually just included a few more galaxy facts about this, but they're not really relevant to this talk, so I'll skip through them. So next I'll talk about a very rare class of stars called Wolf-Rayet stars. When I say rare, I really mean quite rare. I told you that there were about 40 billion stars in M33, and as far as we know, there are only around 200 of these stars in the galaxy total. We're still looking, but as far as we know, there's very few of these in M33. Something interesting about these stars is that they're called emission line stars. In general, when we take spectra of stars, we see absorption lines, but there are a few rare classes of stars that show emission as well, and these are one such class. In addition to being rare and interesting, they hold a special part in stellar evolution. So we're thinking that Wolf-Rayet stars may be an intermediate stage between massive luminous O-type stars and their eventual fate, type 1 BC supernovae. So that's very interesting as well. Something we can use to characterize these objects are the strong stellar winds and high mass loss rates that they have. So as you can see from this picture, the Wolf-Rayet star will be the star in the center of this beautiful bloom. And the bloom is kind of representing this expanding bubble of ionized gas. So basically the star is ejecting material from its atmosphere and exposing the stellar core. And all of that stuff is basically the atmosphere being pushed away from the star and ionizing material in its path. So with that, I'll jump into observations because the very first observation that we have is a good indication of that expanding bubble that I was just mentioning. P Cygni profiles are something that we use as a telltale sign of something like this going on. If you'll take a look at the left-hand side here for the diagram, imagine that the star is right here in the center of this colorful circle. And this is kind of the expanding bubble of atmosphere coming out of it. And the observer, I'll note, is just right over here. So because the absorption region will be coming towards us, it will be blue shifted because of the Doppler shift. And because we can't see the other side, it's actually preferentially got a blue shifted absorption on one half of the emission line, kind of cutting out a chunk of the entire emission from the expanding bubble itself. That's kind of the origin of this profile. And as you can see over here on the right, we see one of these in our Bell spectra. In fact, we see many of them. This is just one example. All of the bells have these profiles and all of them have several, as a matter of fact, mostly on helium-1 lines, if you happen to be interested. Another thing we can use to characterize the bells is broad emission of any kind, but especially in H alpha. We noticed initially when we discovered these objects, quite by accident, that they had a number of broad emission lines, including H alpha. And as you can see from the leftmost plot and the center plot, there's a very broad component to this emission. And we can use that to characterize the speed of the velocity dispersion. So the width here is roughly around 300 kilometers per second. So we can get a sense of what's going on from that number. Although many of the bells, in fact, almost all of the bells show this broad emission, you'll see that Bells 3 on the right-hand side doesn't really show this. And that's kind of a mystery to us because it shows a lot of the other characteristics that we see for these bells, just not this. So we're looking into that, but I don't currently have an explanation for it. This is the real kicker. We were taking spectra of these in 2018, and we decided to follow up on a few of them in 2022. And between that time, we've actually discovered some new Wolf-Rayet emission from one of the sources. We're still looking at the others, but from one of them, for sure, we've seen something new. So I'll call this object Bells 1. As you can see from the left-hand plot, there are 3 emission features, 2 kind of grouped together. Those are nitrogen 3 lines, and then one standing on its own, which I believe is a helium 2 line. That's from 2018. If you look to the right-hand plot, in 2022, we look at the same object and we still see those same 3 emission features, but there's another one that's cropped up in the middle. We believe that this line, this kind of narrow one jutting up, is either a carbon 3 line or an iron feature, both of which would be associated with Wolf-Rayet emission. So that's really, really interesting that we've been able to see an actual change in the spectrum of the object in just 4 years. So with that, I'll jump quickly into conclusions. I'm sure I'm running out of time. We believe this might be the first observation of a Wolf-Rayet star evolving in real time. We don't think that it's been seen that the spectrum will change for these Wolf-Rayet stars, although we do know that they exist on a rather short time scale, so we expect to see somewhat rapid changes. In addition, I actually went into the literature and I tried to identify these objects and see if they'd been previously categorized. And in fact, several of them have been categorized not only as Wolf-Rayet stars, but as an even more rare subclass of Wolf-Rayet stars, which are thought to be in transition from their O-type progenitors into a full Wolf-Rayet star. So we may be looking at an object that is in the middle of transitioning from a hot O-type massive star into this special rare class in M33. In addition to the Wolf-Rayet emission, we can also track all sorts of other changes. We can look at the differing strengths, widths, shapes, and Doppler shifts of several other lines, but I'm not going to get into that in this presentation, and we've got a lot more work to do on that front anyway. Finally, I'll finish up with some of our future work. We're going to keep monitoring these sources. We have 7 bells altogether. We only have follow-up spectra for 3 of them at the moment, but we're hoping to slip them into concurrent observing proposals in the future. And in doing this, we're hoping to track the timescales on which their spectra change and also confirm previous detections of Wolf-Rayet stars, confirm their classifications, and potentially identify some new sources as well. Also, with our use of DEMOS, we're able to reach wavelengths that are slightly longer than many of the previous Wolf-Rayet studies. So we're hoping to further categorize and understand the infrared emission of these sources as well. Thanks so much for listening. This is really exciting work for me, and I hope you'll reach out to me at my email and ask some questions. Thank you very much.
All right, take it away, Jim.
Morning, everyone. I'm Jim Jackson. I'm the director of the Green Bank Observatory. I'm here to tell you today about triggered star formation in the Nessie Nebula. This is my favorite object on the sky, and you can see it there in all its glory. It's this long, sinuous infrared dark cloud. Infrared dark clouds are the birthplaces of stars. And so one of the interesting and open questions remaining in the field of star formation is what happens when a star forms and ejects energy into the surrounding medium? Does it make new stars, or does it prevent the formation of new stars? Do I advance? Pad? Oh, there we go. Okay. Oops, there we go. All right, so what do we know about star formation? So stars form in these very dark, very cold, and very filamentary clouds. This was one of the major discoveries of the Spitzer and Herschel space telescopes. We used to think of these star-forming clouds as spherical blobs. They're not. They're long and snaky. And this picture you see is an image from the Spitzer Space Telescope. On the left side, you see the dark, sinuous clouds that are the birthplaces of stars. If you can see those little red dots, that's where the baby stars are forming. Now, when a high mass star forms, and by high mass, I mean a star that's about 8 times the mass of the sun or larger, they have so much more energy than the sun, and they inject this energy into the surrounding material, and they form these bubbles, much like the bubble that Olivia was talking about, although her bubbles are bigger. These are still pretty substantial bubbles. And they ionize the gas around them, and they inflate these bubbles, and the bubbles expand. So these objects are called H2 regions. And on the right side of this image, you can see the NGC 6334 star forming region, also known as the Cat's Paw Nebula. And you can see a large number of these bubbles. And you can see that there's a lot of energy associated with it. They're stirring up the gas around them. And the question that I'm trying to answer is, does this energetic feedback trigger or hinder the formation of new stars? And you can imagine this going both ways, right? If the bubbles are just dispersing the gas, that gas is gone and no stars can form. On the other hand, if you have a clump of gas that's almost ready to make a star, but not quite there, and you hit it with a expanding shell and compress it, it can push it over the edge and gravity can take over. And so those are the kind of ideas that are out there. Some people say you make new stars and some people say you don't. So here's the Nessie Nebula. Nessie is the largest filament that we know of. It is over 100 parsecs long, and it is a glorious object. I first encountered Nessie at a AAS meeting about 15 years ago in St. Louis. We had just finished the Spitzer survey of the galactic plane called Glimpse. We had these big posters along the wall of the exhibition hall. And I remember walking past this thing and it just kept going and going and going. It was about 15 feet long. And I said, what the heck is that? And I'm still wondering, what the heck is that? Studying this has been a real pleasure. All right, so what's cool about Nessie is, apart from its very stringy nature and its length, it has a large amount of mass. There's about 600 solar masses per parsec, and that little yellow scale bar shows you 1 parsec. So every chunk of that cloud has plenty of mass to form stars. Right? It is cold, dense, and opaque, and it is a very large object on the sky. So if you were to compare the size of Nessie with that of the full moon, it would look like that. So it's larger in extent than the full moon. All right, so let's see whether or not these bubbles can do something to make new stars or not make new stars. So I'm going to focus on the Nessie bubble there on the right. There it is in all its glory. And if ever an object in space were crying out for understanding, it is this one, because it is shaped like a question mark. All right, here's another image of Nessie. This is a mid-infrared image with a slightly different color scale, slightly different wavelengths, but I wanted to show this image to clarify what we think is happening here. So let's zoom in on the bubble on the right side. And what's happening in the bubble is you have hot stars right there. And those hot stars are forming a bubble. And they're driving this expanding bubble into the interstellar medium. So there's the expanding bubble, which is the crook of the question mark. And now extending through, that's the Nessie filament coming through on the other side of this bubble. So the bubble formed in Nessie and blew a bubble into Nessie and is now interacting with it. So there's the Nessie filament. And if you notice, right at the tip of that filament, there's this green thing. And that is a luminous protostar. So this is a baby star in its very earliest stages of formation, and it is one of the brightest that we know of. It's one of the most luminous. So this was known, the phone number there is AGAL 337.916 minus 0.477. There's the expanding bubble, there's the luminous protostar there in the contours. This is an image from the Atlas Gal survey of dust continuum emission. And there's the filament. And this protostar sits right at the end of the filament, right where the bubble is hitting the filament. So that's really strongly suggestive that the filament interaction with the bubble created the star right at that spot. So triggered star formation. Right? Now, we don't know for sure. It could be a chance projection. We don't know really. So we need to find real telltale signs, the smoking gun of an interaction between the expanding bubble and the filament. So to do that, I use 2 different observatories. One, the Sophia Observatory, which observes in the infrared, far infrared. And for that, I used Sophia to image partly ionized gas. I also use the Australia Telescope Compact Array, which is a radio telescope near Narrabri, New South Wales, in the best of all countries, Australia. And that probes ionized gas through the radio continuum emission. It probes cold molecular gas through emission from an ammonia line. And it also probes warm molecular gas through the emission of another ammonia line at higher energies. Right? So let's see if we can find the smoking gun that shows that there is indeed interaction between the bubble and the filament. All right, so this slide's a little busy, but let me talk you through it. And I think you can see my cursor here. So right there, we have our hot stars, and this is the thing that's lighting up the expanding bubble. The radio continuum is this blue. Let's see if I can pull it there. This blue is radio continuum, which shows the fully ionized gas. So this is gas that's lit up by the full blazing glory of those hot stars. The green contours, let's see, just outside that, that's the C+ emission, and that's partly ionized gas. And you would expect, oops, backwards there. You would expect the partly ionized gas to be further away from the hot star. So what happens is the radiation from the hot stars becomes attenuated by the dust, and not much of it survives. And so you go from a fully ionized state to a partially ionized state, and then into a fully molecular state. All right, so that's all well and good. That's what we expect from gas lit up by a hot bubble. And then in the black, you see the filament. So that's the ammonia 1,1, which is probing the cold molecular gas, and there's the filament. And X marks the spot. There's the protostar right at the end of the filament. What's new here in the smoking gun, and I'll show you in a minute, this is indeed a smoking gun, is the red. And that is the warm molecular gas traced by ammonia 3,3. That's the telltale sign of the interaction. You see it lies right where the bubble and the filament are intersecting. All right, so let's look at that a little bit more. So the ammonia 3,3 traces the warm ammonia gas. The 1,1 traces the cold ammonia gas. So here's the cold ammonia gas. And you can see the filament extending off to the right, and that bright blob in the center is the protostar. Okay. Now let's change to the ammonia 3,3 and see if you see any differences. Yeah, you see the protostar still there, but now you see these two new things. And it's very, very unusual to see ammonia 3,3 when you don't see ammonia 1,1. That's a telltale sign of a shock interaction that's being slammed by some supersonic flow. So well, there are two sources here. There's on the left, you see the hot spot, and there's the spectrum to the lower left of the slide. And the blue there is the ammonia 3,3, and it is much brighter than the ammonia 1,1 in red and the ammonia 2,2 in green. That's very unusual, and that indicates a shock. Even rarer is the thing on the right, and that's an ammonia 3,3 maser. When you tickle ammonia 3,3, well, tickle it, when you slam it actually, when you slam ammonia 3,3, it has to compress and get really hot. And if it's right around 200 Kelvin and very high densities, you can invert the population of the ammonia molecules and make a maser. Exactly the same thing as the laser, but at microwaves. So that's what the M stands for. All right. And this the telltale sign of that, no other ammonia emission and a very narrow spectral line. And that's what you see in the spectrum there. The blue is the ammonia 3,3 maser. Okay. So we have our definitive evidence. The warm ammonia hotspot and the 3,3 maser are these definitive telltale signs of a shock. And what that means is that the gas from the expanding bubble is slamming into the filament at supersonic speeds and heating and compressing it right at that spot. Now, the Nessie filament, as I mentioned, is really dense, has a lot of mass. It's poised to collapse into new stars. And so the collision with the bubble has compressed that and caused gravity to win, and that material then can collapse into a protostar. It's pushed it over the edge. So the formation of the luminous protostar was indeed triggered by the bubble filament collision. And what's kind of cool about this is it suggests a scenario where you have falling dominoes. So a star makes a bubble that makes another star in the filament, which makes another bubble, which makes another star. And you can imagine star formation kind of propagating down the line of the filament like dominoes falling. And if you remember my first image of NGC 6334, that's exactly what you see is a bunch of bubbles spaced down the filaments. Now, I do want to mention that I'm not the only one who did this work. I have an international team. Here they are. I wrote the proposals, but they did the heavy lifting and did much of the work. And I'm just reporting their work for you today. So I'll end with my conclusions and thank you for your attention.
All right, I think you're all set.
Hello, so I'm Stephen Walker from the University of Alabama in Huntsville, and today I'm going to talk to you about our work on new Chandra observations of this infalling group which is falling into the galaxy cluster, the Coma galaxy cluster. So clusters of galaxies are the largest gravitationally bound structures in the universe, and they're so big that they're still continuing to form. The universe is not old enough for them to have finished forming yet. And what you're seeing here is a computer simulation of this structure formation happening. Galaxies and galaxy groups are merging together to form galaxy cluster. But what you're seeing is taking place over hundreds of millions of years. And obviously we don't have the luxury of waiting hundreds of millions of years to see this formation happening. But can we do something? Can we do an observation, actually see this structure formation happening? So here is our target. This is the Coma cluster. We can see in this image, these are the two brightest galaxies in this galaxy cluster. But this image alone gives us a little understanding of the dynamics actually at play here. How are these galaxies moving? This improves if we look in the X-ray. So I'm going to superimpose the X-ray image onto this. And we can see immediately is this structure in the bottom right here, which is an infalling galaxy group called NGC 4839. And behind it has this long tail. It's around 1.5 million light years long. So where are these X-rays coming from? So the X-rays are coming from a very hot plasma that fills galaxy clusters. It lies between all of the galaxies, and it's actually where the majority of the normal matter, the baryonic matter, lies in galaxy clusters. So it's important to understand the properties of this really hot gas. So yes, has a temperature of around 100 million Kelvin, and that allows us to study it because it glows in X-rays. And it gives us a pathway to seeing the motions of galaxies and galaxy groups happening. And a fun fact, this structure, so one of the cool things about the Coma cluster is that it's relatively nearby. And in terms of galaxy clusters, relatively nearby means 330 million light years away. So in my work, that's quite nearby. And this tail, because it's so big, 1.5 million light years, if you had X-ray eyes and you looked up in the sky, this tail would be just slightly smaller than the size of the full moon. So it would be very spectacular if you had X-ray eyes. It would make my science much easier if we had X-ray eyes. So, what we did in this was to do an in-depth Chandra observation just of this infalling galaxy group. So we can see features here. We've got the head, which is where the main galaxy of this galaxy group lies. And then we've got the tail, much like a comet tail, coming behind it, only it's super hot plasma that's coming off this thing. And yes, the Coma cluster's proximity, its nearness to us, allows us to do the most in-depth study yet performed of the structures going on as gas is being stripped from this galaxy group. So the clusters studied before now have been much further away, and they're too far away to actually see fine structures of what's actually going on. One thing that we've been able to observe is that in front of this galaxy group, marked by that white curve, appears to be a shock front, and that indicates that this is moving at a speed of around 3 million miles per hour. So this shock front is analogous to the sort of sonic boom that you would get from a jet airplane, only instead of traveling at a few thousand miles per hour, this thing is traveling at 3 million miles per hour. Yeah, and we see that the tail coming up there. So another thing that the Chandra data allowed us to do, we could run an edge detection filter, which will enhance features in this. And so I'm about to show this edge detection filter here. What you can see is that it reveals a sort of bump feature here. So the edges of the tail are not smooth. And we believe this bump to be produced by a type of instability, which is called the Kelvin-Helmholtz instability. So we see these Kelvin-Helmholtz instabilities whenever you have a velocity shear, basically meaning a gas flowing on top of a gas. And this is exciting because we can use this infalling galaxy group to probe the properties of the intracluster medium of this super hot 100 million Kelvin plasma. It would be great if we could just get a cup of this plasma and just swirl it around and understand its basic properties, but it's so far away, we obviously can't do that. So nature has to do this, the swirling for us. So here we have a computer simulation, 2 computer simulations of an infalling galaxy group. And the difference between them is the level of viscosity in the simulation. So viscosity is basically the level of runniness of a liquid. So a low viscosity means that, like water, means it will flow very easily, whereas a high viscosity, but like honey, means it will flow less quickly. And so I'm going to play these 2 simulations, and we're going to notice differences between them. And I'm going to pause it around here. So what we can see in the low viscosity simulation at the top is that the level of Kelvin-Helmholtz instabilities formed is very high, and they tend to have this sort of hook type structure, which is not what we observe. If we boost the viscosity a bit in the bottom, what we see is that these instabilities have a different type of shape. They're more like bumps than hooks. And this is closer to what we actually observe in our observations. A second thing that is different between these simulations, if I allow them to play, is the length of the tail that is produced behind them. So I'm going to pause it here. We can see in the low viscosity, oh dear, try again. I knew it was too good for it just to work first time. Here we go. I want to pause it. Yeah. Well, we can see that in the low viscosity case, the tail is very short. So whereas in the higher viscosity case, the tail is much longer. So there are 2 prongs of the attack that we can do to probe the viscosity. It's the level of the Kelvin-Helmholtz instabilities, and it's the length of the tail behind. And I've already shown that the length of the tail is over 1.5 million light years, so it's very, very long. So this gives us a unique and probe of being able to understand the properties of the gas between galaxies and galaxy clusters. So this is a summary. The Chandra has allowed us to study how galaxy clusters grow through mergers. In particular, we've studied this tail behind this infalling galaxy group NGC 4839, moving over 3 million miles per hour. And by the proximity, the closest of the Coma cluster, has allowed us to explore for the first time in fine detail levels of instabilities, turbulence that's produced in this tail. If you want to know more, then there's a link to the paper here. I also want my contact details at the bottom, and I also want to plug Mohammed Mirakor, who's right here, who did a lot of the data analysis on this. I was PI, but he did a lot of the making pretty pictures and so forth. And thank you very much. Thank you.
All right, with that, we can get started with our Q&A. I am just going to switch things around on the screen to bring Olivia back into view quickly. Oh, I've lost the ability to not be screen sharing. Oh, Zoom, why do you do this to me? But if there are questions in the room, we can start with those while I figure this out.
And kindly identify yourself and your affiliation.
Hello, Melissa Lehue, Troy Astronomy Club in Alabama. This question is for Mr. Walker. And please forgive me for this very elementary question, but you mentioned that the galaxy is moving at 3 million miles per hour. What methods do you use to detect the exact speed?
Yeah, so in front of the galaxy group is that curved feature, it's called the shock front. That's produced whenever you travel faster than the speed of sound in a medium. And the speed of sound is something that we can calculate. Basically, you just need to know the temperature of the gas, which we can measure from the X-ray data. So that gives us the speed of sound. And basically the size of the jump in the image, basically the contrast between the gas in front of the shock and behind the shock allows us to measure how fast it's moving relative to the speed of sound, and we get it to move about 1.5 times the speed of sound. So that puts it at about 1,500 kilometers per second, which is about 3 million miles per hour. Yeah, so that's how we do that. It's basically by measuring that shock front in front of it.
Hi, my name is Coral. I'm a recent graduate of Lake Forest College, and I have a question for Jim. Out of curiosity, have we seen a filament in our local area from our star formation? I know it was 5 billion years ago, so I just wanted to know.
So the nearest filament is the Orion filament, which is associated with the nearest region of high mass star formation, the Orion Nebula. That's about 450 parsecs away. Nessie is about 3.5 kiloparsecs away, so 6 times further. Nessie is in the kind of the nearest spiral arm in that direction.
Do we have more questions in the room or online? Yep, okay.
All right, we have a few online. This one is for Olivia from Bill Waller of the Galactic Inquirer. He wants to know, what are the nebular contexts for your Wolf-Rayet stars, H2 regions, etc.?
That's a great question. We definitely think that they are in H2 regions. We see some nebular H alpha emission, and for that bells that didn't have the broad H alpha emission, there's like the very typical H2 region with like a H alpha spike and then the N2 doublet on either side. So I definitely would say that they're in H2 regions.
This one is from Monica Young of Sky and Telescope for Jim Jackson. She says, good to see you. So you found an excellent example of collision-triggered star formation, but what would you need to show that collisions and shocks generally do formation versus disperse the gas? Simply more of these types of objects?
Yes. Hi, Monica. Nice to see you virtually too. Yeah, I guess you would. So what the problem we have with the high mass stars, as you could see from the first slide I showed, was they're so disruptive, they blow up their environment right as soon as they form. So it's really hard to capture these sorts of interactions before the disruption occurs. Eventually, they will disrupt the material around them. But we do see, for instance, in the shells of H2 region, we sometimes see stars forming in the rims. But this is the first example I know of a shell or filament bubble interaction. Now, the nice thing about this is that the bubble is hitting a region that's already primed. It's like a landmine, right? You're stepping on it and off it will go. So I suspect the reason that we see these chains of bubbles in these filamentary clouds is exactly this. Now, what we need to do to prove this, we would need more examples of this sort of phenomena. So we have to look at other filaments. There are about a dozen other bubble filament systems where it looks like this is happening. So this can be addressed.
Sure. We have another. This one is for Olivia from Matthew Gregory Henson. He wants to know, how many light years away from Earth is M33?
Another great question, and I have an easy answer. 2.73 million light years or so.
And one more from Bill Waller of the Galactic Inquirer. This one is for Jim Jackson. Did you find any evidence for shocked molecular hydrogen at the bubble filament interface?
Haven't looked for it yet, Bill. I would bet it's there. There is an indication of it in the Spitzer image. You see that kind of green spray? That's typically caused by shock-excited molecular hydrogen. It's there, but we haven't done that ourselves.
Great. If there are no more questions online and in the room, I have a couple. The first one I have is for Olivia. Hi, this is Kerry Hensley from the AAS. So you mentioned that these stars are incredibly rare, giving the example that there's only 200 of them among like many, many millions in M33. So I know there are a lot of cases in astronomy where rarity really means it's very short in terms of time. So I'm curious about what the time scale of the transition is between O star and Wolf-Rayet star and then on to supernova.
That's a fantastic question, and I think it is the next one I'm prepared to ask for this work. It's definitely true that because there's such rarity for these objects, we assume that they exist for a very short time, much like Green Valley galaxies. I'm also a galactic astronomer. And so we expect the timescale of change to be very quick. And the fact that we're seeing a change in the spectrum in just 4 years also suggests that. So those two things tend to agree. But I did a quick literature review and I wasn't really able to find anyone making any claims about the timescale, just that we expect it to be rapid. So that's a great question. I don't know.
Great. Well, thank you for your answer. And I look forward to a more thorough answer in a future press conference from you. I have another question for Jim. So this is probably a very naive question as someone who is not a radio astronomer, but you mentioned the importance of seeing ammonia 3.3 emission tracing the hot gas and not seeing that ammonia 1.1 emission tracing the cold gas. Is there an opportunity to take like difference images of those two? Okay, I'm already getting a nod, so I'm on the right track. But yeah, is that another way to find these instances of star formation?
Yeah, it sure would be. So there are ammonia surveys that have looked at both 1.1 and 3.3. I've done some. Gaunt has done some. The Hops team, Andrew Walsh, has done some. And, you know, we're still pouring through these data, but yes, a telltale sign of these shocks would be finding either these 3.3 masers, which are just very bright, they're amplifying the background, or to look for regions where the 3.3 is much brighter than the 1.1. That's easy to do. And it's the subject of future work.
Excellent. I will expect another press conference from you as well then. All right, do we have any more questions here in the room or online? If not, we can wrap things up here and give you a chance to get to some other sessions. Really big thank you to everyone who joined in person, online, and on YouTube, and to our PIOs who helped to prepare press releases for the session, which shared on the AAS Press Office Twitter account on the AAS website, and we'll also share those on the Slack channel. We will be meeting here again today at 2:15 p.m. to hear about hot Jupiters and hungry black holes. So I really hope to see you then. And with that, let's give our presenters one last thank you.